Hi, everyone. My name is Hao Huang, a PhD student from Texas A&M University. Today, I'm going to present our paper toward efficient wide area identification of multiple element contingencies in power systems. In this paper, we use the line outage distribution factors to formulate new metrics, the NLODF and M, to represent the importance of branches in the system. We use the group betweenness and the centrality to identify a set of the most critical elements in the network whose loss has a severe impact to the system. In this paper, we propose a new framework to identify the critical branches in power systems with new introduced parameters, distance, searching level, and number of contingencies, dx. First, we use the power system information to compute the LODF for each branch, and then calculate the NLODF and M for all branches to evaluate their importance. And based on the rank, we choose the top alpha% branches as critical branches we want to analyze. And with the distance D, we will choose other high impact branches that are D hop distance close to the critical branches to formulate a subset. For that subset, we will extend the graph based on the search level to find the other nodes or branches in the system to formulate the subgraph. And for each subgraph, we will use the group betweenness and centrality to select the most critical X branches. After that, we will run the contingency analysis to examine their impact to the system. Here is an example of how we construct the subgraph with the distance and the search level are both equal to 3. The green star nodes here are the most critical line in the system who has the highest M value. And then with the distance, we choose other high impact branches in the grid that are within 3 hop distance to the green star nodes. After that, based on the searching level, we find all the red triangle nodes. All the colored nodes formulate the subgraph we will explore. In this paper, we apply our framework to 2 synthetic grids. The first one is 200 Pascals, and here's the result with the distance and the search level are both equal to 4. Compared to our previous algorithm, the new framework finds more critical combination of branches, which are highlighted in green. We also look into the computation time regarding to the searching level and the distance, and we find the computation time is almost linearly increased with those values. For the 500 bus case, we find more critical branches under different distance and the searching level. And here is the computation time graph. And for the 500 bus case, we find out the searching level is more sensitive to the distance regarding to the computation time, since the searching level determines the number of neighboring nodes, which impact the formulation of subgraph. To sum up, in this paper, we provide a computationally tractable approach to identify critical components, which is branch in our paper, by exploring the group betweenness centrality and LODFs. In future, we will improve the framework's efficiency and speed by choosing appropriate parameters for distance and the searching level, and also implementing parallel computing to speed up the framework.